Hello, my name is Catherine Champagne, and I am at the Pennington Biomedical Research Center in Baton Rouge, Louisiana. I have been here for 33 years, and right now it's a bright and sunny day in Baton Rouge. Rather hot. It will be approaching the 90s, so if you're coming to Baton Rouge, August will be awfully hot. So I am pleased to be able to moderate this session 2, Advances in Nutrient Metadata for Dietary Assessment. Our first speaker is Alanna Moshfegh. Alanna is a master's trained person and the research leader for the Food Surveys Research Group at the Beltsville Human Nutrition Research Center in the U.S. Department of Agriculture. And she was referred to in our last session, so I'm sure we're all looking forward to hearing her words of wisdom. Her talk is entitled Gateway to Advancing Nutrient Profile Calculations in FNDDS. Our second speaker is James Harnly. Dr. Harnly is an analytical chemist with more than 40 years of experience in industry and government. And he will be talking to us about variability in foods, the logic behind foundation foods. Our third speaker is Linda Cantor. She is an agricultural economist in the Diet, Safety, and Health Economics branch of the Food Economics Division at USDA's Economic Research Service. And Linda will be talking about using the ERS food purchase groups to access the healthfulness of food purchases and acquisitions. And our final speaker is Edwina Wambogo. She is a PhD in nutrition and a Master's of Public Health and Community Health Education from the University of Maryland. And she is a nutrition epidemiologist with the National Center for Health Statistics at the CDC. And her talk will be potential bias of nutrient intake estimates due to using non-synchronous versions of USDA's Food and Nutrient Database for Dietary Studies, and HHANES 2015 to 2018. And so with no further ado, we shall start our first session.
Good afternoon. I want to thank the program committee for the opportunity to present on the Food and Nutrient Database for Dietary Studies, with a focus on the work at the Food Surveys Research Group and how we are advancing nutrient profile determinations in FNDDS. Before I start, I must say to my colleagues and friends in Canada, I do regret we're not in lovely Ottawa at this conference, but look forward to it being held there soon. In the time I have with you this afternoon, I'll cover 3 areas. Give a brief overview of FNDDS, discuss its relationship to Food Data Central and the impact Food Data Central has had on FNDDS, and share a few strategies we're using in nutrient profile determinations for FNDDS. With any database, it's important to understand its purpose, why it is developed. For those not familiar with FNDDS, it's the application database used to determine the nutrient profile of foods and beverages reported in what we eat in America, the dietary intake component of NHANES, the National Health and Nutrition Examination Survey in the United States. FNDDS is a companion component to USDA's 24-hour dietary recall instrument, the Automated Multiple Pass Method, or AMPM. Together, the FNDDS and the AMPM form the 2 pillars of dietary surveillance in the United States. In addition to nutrient profiles, FNDDS provides further understanding about the foods and beverages reported in the survey. It's updated and released every 2 years in concert with the What We Eat in America survey data release. Each new FNDDS version reflects 2 things: updates made to the AM/PM recall instrument and new composition data in Food Data Central. And changes are extensive with each FNDDS version. First, the number of foods in the database change over time. This slide shows the number of new codes added and codes discontinued across 4 versions of FNDDS. The 2019-2020 FNDDS is the 10th version of this database. It's not yet released, but my talk will incorporate a few facts from this latest version. A presentation specifically on FNDDS 1920 will be given in session 8 on Wednesday afternoon by Donna Rhodes, so be sure to tune in. The changes in codes do reflect the AM/PM review and update. With each 2-year collection of What We Eat in America, we review between 10 to 20 pathways in the AM/PM recall instrument in order to enhance questions and probes, which results then in changes we make in FNDDS. The review focuses on a variety of aspects unique to the individual pathway, but across all the AM/PM pathway reviews, the foremost areas are the respondent, the food or beverage, and their nutrient content. So, what accounts for adding and discontinuing codes? Some examples. New codes are added if a food was previously collected by its components, such as for sandwiches. We used to collect each item in most sandwiches: the bread, the filling, what was added to it, like tomatoes, a spread, etc. In recent versions, we've added a number of new codes for what we call single code sandwiches. Another reason a code is added: if a code for one type of food was expanded to more codes representing more types of that food, such as yogurt being expanded to regular yogurt and Greek yogurt. Likewise, the opposite can happen. Codes are discontinued when multiple codes reflecting different types of a food are consolidated to one code. Codes are also discontinued if they have not been reported in the survey over several survey cycles, probably reflecting that the food is no longer in the marketplace. Another factor in adding and in discontinuing codes: no code number is reused. For more details on discontinuing codes, I'd urge you to visit a poster on this topic by Jim Friday from the Food Surveys Research Group. Now, let's move to the ingredient codes used in FNDDS, which are mainly from Food Data Central. They have changed over time as well. These 2,447 ingredient codes are applied in a variety of protocols and strategies to generate nutrient profiles in FNDDS. So ingredients, their source, how we put them together, are really the key to the nutrient profile. For a third of the FNDDS codes, the match to an FDC code for an FNDDS code is straightforward. It's one-to-one, such as for whole milk in FNDDS is matched to whole milk in Food Data Central. The remaining 2/3 are matched to multiple FDC codes to generate nutrient profiles. It is in this area that I'm going to focus on our strategies. This combining together, or recipe calculation process, as we call it, is used when there is not an available or appropriate FDC item for the FNDDS food or beverage. So let's delve into this recipe calculation process a bit more. It can be briefly summarized in 3 steps. Select each ingredient and its amount. Apply adjustments if necessary for factors such as yield, nutrient retention, or moisture adjustment. And these are based on the form of the ingredient, if it product has to be cooked, etc. And sum the resulting nutrient values to yield a nutrient profile. This produces a nutrient profile that represents an average of variance of a food or beverage, not an exact product. FDC codes are selected to create a nutrient profile. They are not necessarily the exact ingredients that one would find in the product. Ingredients that have minimal nutrient content, such as spices, are not included in this process. And the nutrient values may be supplemented or adjusted if needed, and I'm going to explain that in a little later. Thus, these are not cookbook-style recipes, but rather calculated nutrient values of ingredients to create a nutrient profile. These next 2 slides will show the source of the ingredient codes in FNDDS over these 4 versions that you see on the left side of the graph. Use of standard reference codes has decreased by 1/3 across these FNDDS versions. That makes sense, with SR Legacy being the final release of standard reference in 2019. Since the launch of Food Data Central in 2019, we're utilizing as many of the foundation foods as we can to build FNDDS nutrient profiles because they reflect more current analytical data. The last 2 types of ingredient codes in FNDDS represent the strategies we are advancing in developing nutrient profiles. The gold bar represents FNDDS codes that serve double duty. They're used for food reported in What We Eat in America and also serve as ingredients in recipes. And the red bar represents what we call FSRG derived codes, 44 of them in the 2019-2020 FNDDS. Looking across the different types of ingredient codes, while most are from Food Data Central, specifically Standard Reference Legacy and Foundation Foods, these 2 other types of ingredient codes are increasing. In the next few slides, I'm going to give insight about the strategies behind these 2 types of codes and their benefit in surveillance and in building FNDDS nutrient profiles. The strategies I will describe include 2 types of FNDDS codes: generic, and those used only in recipes, and 2 types of ingredient codes for nutrients and for lower sodium products. The first strategy is FNDDS codes that represent generic foods, such as the example for milk, not further specified, or NFS. The milk NFS code is used when a survey respondent does not know the type of milk they drank or had in their coffee, as example. It is also used as an ingredient in a number of recipes in FNDDS that include milk. The proportion of different types of milk by fat content that you see here on this example are based on market share data from USDA's Economic Research Service. The other example, the pickles NFS code, is used primarily when a respondent reports a sandwich with pickles. The type of pickle does not have to be asked, and that reduces respondent burden. Why? Because What We Eat in America data shows that on a given day, half of Americans report consuming a sandwich. Now, these are examples of generic codes. I don't want you to think these are the only 2 codes that represent milk or pickles in FNDDS. Nearly 70 codes for milks, both plain and flavored, are in FNDDS, and 30 codes exist for pickles, olives, and pickled vegetables. Now, this strategy of generic foods benefits both surveillance in reducing respondent burden and our work in recipe development standardization, and demonstrates, I think, that unique relationship that I've talked about between FNDDS and the AMPM. The next strategy involves FNDDS codes we have created that are used only in recipes. They're not used in reporting a food from the survey. There are 28 such codes in FNDDS for 1920. They all begin with 9 as the first 4 digits. These 2 examples you see on the slide show the ingredients used in FNDDS codes for single code sandwiches. The cheese as an ingredient in sandwiches reduces the questions that need to be asked when a survey respondent reported a sandwich with cheese. The wheat bread as an ingredient in sandwiches also reduces the questions that are asked if the respondent reported a sandwich made with bread that was made with whole wheat or whole grain type of bread. We know the public has difficulty, I have difficulty, in accurately determining what are whole grain products. Our survey experience shows, and it's been documented in scientific studies, that people often mistake bread that is brown in color as being whole grain. So this type of code, ingredient code, addresses that challenge. The next strategy is adding ingredient codes that are specific for a single nutrient or a composite of nutrients. These codes contain only an amount for the nutrient or the nutrient composite. There's zeros for all the other nutrients that are assessed in the survey. There are 7 such nutrient ingredient codes in FNDDS 1920. We use these to meet the nutrient profiles for assumed fortification of commercial products. That being vitamin D in regular yogurt and baby food yogurt, and the other nutrients in ready-to-eat cereals. To generate a nutrient profile for a fortified food product in FNDDS, using basic ingredient codes from Food Data Central for the grain ingredients of cereals such as oats or corn, and of course a few other ingredients depending on the type of cereal. The strategy of nutrient ingredient codes was a necessity to get to the fortification level of the nutrients. In Donna Rhodes' presentation on Wednesday, she will detail the ready-to-eat cereal fortification protocol that was developed. The last strategy I will discuss is adjusting one nutrient, sodium, within a Food Data Central code. Sodium was lowered for these ingredient codes to reflect the food industry movement of lowering sodium in their products. The strategy is used, as you can see here, for meat and poultry deli items and tomato juice. In closing, I've given you insight about the purpose of FNDDS and the strategies we are advancing in determining nutrient profiles in this database. This is a website address for the Food Surveys Research Group where you can access the publicly available FNDDS versions, the most current being 1718, and of course where you can look for the 1920 when we release it. I want to gratefully acknowledge the FSRG staff you see here at the bottom of the slide for their tireless contributions in the development of the 1920 FNDDS. Thank you for your attention.
Good morning. I'm Jim Harnly. I'm with the Department of Agriculture. Today I'd like to talk to you about the variability in foods, specifically the logic behind foundation foods. Foundation foods is one of our new database types associated with Food Data Central. Its purpose is to look at variability, as I will discuss in the following talk. Most sciences will say, refer to signal to noise in any measurement or any concentration, whereas the signal to noise indicates a detection limit, and it generally indicates the reliability of a signal. So in nutrition, signal is going to be the food concentration of a specific component, and N will be the variability of that component, and it has a number of sources. The variability in foods can originate with genetics, environment, management, processing, and I've added another P, preparation. So variability usually refers in most cases to individual components, although in this talk I will talk about multivariate analysis and multivariate variability. So is variability important? Some people say no. Over the course of a year, people will eat many servings of the same food, and the intakes will average out, so the variability is unimportant. However, many of us say yes. Basically, because all foods are not equal. You never analyze the one you eat. We also need variability data for research. Complete analysis of feeding studies. It's not sufficient to use a database. You have to analyze the foods that are being eaten. Epidemiology also requires full characterization in order to have validity. Identification of adulteration is needed, has need of information on variability to decide if something is out of limits or exceeds limits. And if you're going to have precision nutrition, you're going to need precision database, and this includes variability. So here's a good example. This is work done by Professor Elizabeth Jeffrey at the University of Illinois, looking at 3 different vitamin levels. And you can see the mean and you can see the variation. So this doesn't really tell you much And here's one specific vitamin, looking at carotenoids in broccoli as a function of the different genotype on the vertical axis. You can see that there's a tremendous variation. And this really does emphasize the point that all foods are different. These are essentially all broccoli. They're recognized as broccoli. Genetics would characterize them as broccoli, but certainly the vitamin level is dramatically different. So let's start with analytical sources of variability. If you just run one sample, one measurement, one time, there's no variability. Life is wonderful. You don't have to worry about samples agreeing. However, if you take that same sample and repeat it many times, you'll see a variation. And this is the standard deviation associated with that average measurement. Now, if you repeat the preparations, start from scratch with the same sample and do it many times, you get further variability where the preparation introduces variance. If you take different samples of the same material, and again, multiple preps, multiple analyses, you get further increase in variability. And finally, if you have several different labs doing the analysis on these repeat foods, you'll see your greatest degree of variation. But this has to be taken into account when you say, I can analyze this food with this accuracy and this variability. In terms of commodities, the plant materials we'll be looking at with the GEMPP model, again, you can see, take a single plant, analyze it, you got a single number, life is nice. However, if you look at different cultivars, you will see an increase in variability. That was well illustrated for the broccoli. If you grow these plants in different locations, Miami versus Florida versus Washington State, further increases. Management, are these organically grown or conventionally grown? Processing, how is the food processed, stored, transported? These all are a factor and will increase your variability. And finally, preparation. You take it into your house, how do you cook it? Retention values, retention factors as far as the different components. Do you add it to other dishes? Are there interactions? Garlic, for example, you have no glucosinolates. If you chop it up, they all convert to isothiocyanates. So as you can see, by the time you eat a food, there's a tremendous variation in all the components compared to what they originally started from in the original plant. So Foundation Foods evaluates variability. We're looking at single ingredient foods, single organisms, apples, peaches, carrots, whatever. And also we're looking at foods derived from single ingredients. In other words, they're lightly processed. Flours, you don't analyze the seeds, you analyze the flour, the ground version. Commercial milks, they're pasteurized, homogenized. Fruit juices, they may have additives. They're squeezed or forced from the original fruit. Okay, so our foundation food protocol is this. We select a food, we define the food, and there are factors that help in that definition. For example, how much mass do you need to do all the analyses? A single egg won't do, so we defined a egg sample as 3 cartons. Genus or cultivar, do you look, is your food an apple or is it a Granny Smith apple? How specific? It makes a big difference. By age, we looked at bananas, ripe versus overripe. And by size, color, grade, when we did eggs, we did grade A white eggs, not eggs in general. Next factor, next step is to determine sources of variability, the metadata. This is probably the most crucial step and requires a fair degree of research. Cultivar, location, year, farming mode, all the GEMP factors that I listed earlier. Next step is to collect 8 or more samples once we've completed the previous steps. And we may collect these samples on either a retail basis or from an agricultural source. And then we're going to analyze each individually, and we'll report those numbers individually. We will not do composites. Composite is a four-letter word. Okay, so if we're looking at foundation foods, this is going to look familiar. We start with the plant-to-plant variations, cultivar variations, season and location, and then finally processing, transport, storage. Those will all contribute to the foods that are sources of variation that will go into the foods that we have in our database. Okay, if we look at retail sources, we're limited into the variability that we see. In essence, we're stuck with the last degree of variability: process, transport, storage. We may be able to get season and location. Certainly we get season if we do it between different years. Location is more difficult, requires working with the distributor. Cultivar, sometimes that is available, many times not. And certainly plant-to-plant variation is not. If we go to the farmer, to an agricultural source, we can then pick up a lot of the information, sources of variability that fall earlier in the whole preparation process. You can see you might get plant-to-plant, depending on how we collect the samples, who we work with. You'll definitely know the cultivar, what are they growing in the field, and certainly season and location will be well established. Processing, transport, and storage may not be known because if you're working in the agricultural mode, this information has not occurred yet. In many cases, this agricultural source also corresponds to a much higher degree of research. So we generally associate agricultural sources with a research project, and it's more detailed and more difficult sometimes to collect the necessary samples at the level we would like to see represented in a store. And certainly much of this is transparent, or excuse me, not available. This information is not available to the user, to the consumer. Here's an example. Analysis of Rio Red grapefruit, a project from about 10 years ago. We wanted to look at grapefruit, and we were working with farmers. Another fellow at USDA in Westlake, Texas. We could look at different years, conventional versus organic. Each orchard, they harvest early, mid, and late. From each of those harvests, we had 10 samples. And we had 5 analyses, between 3 and 5 analyses per sample. Okay, what did this information give us? What was the significance of those factors that I listed on the previous page? You can see with principal component analysis, and then which follows multivariate analysis of variance, we can see that years were highly significant. The data cluster separately. The farming mode, organic versus conventional, was highly significant, and the time of harvest. So you can see that all 3 of those factors were important to the components in the food, and with multivariate analysis, we grouped them all together to see if they were similar or not. Interestingly enough, that same project also looked at consumer taste panels, and they found differences. Certainly between organic and conventional farming, which was their initial target. People like the conventional better, ironically. The organic farming tend to be a little bitter, a little richer in the flavonoids, which gives a bitter flavor. Here's another example where dry beans were grown in 7 locations. You can see I've labeled them: Washington, Colorado, Idaho, North Dakota, Puerto Rico, and Nebraska. There were 13 components, trace metal components analyzed, as well as total lipids, total protein, starch, and fiber. You put all these together and you look at the multivariate analysis, and this is then principal component analysis, and it shows basically location, location, and location are the primary factors And each of these clusters represents approximately 70 different genotypes. This is just looking at the iron in these dry beans. 6 states, for some reason, we had no iron from the samples in North Dakota. This is a frequency plot. We're looking at the concentration, levels of concentration, and the number of plants, the intensity of the signals at each of those concentrations. This is a little difficult to see. So if you take a look then at just 2 locations, here's Colorado and Puerto Rico. The means and the location are illustrated by the vertical lines. And you can see that basically at a statistically significant level, 95% confidence level, these 2 populations of iron in these states are different. So if you eat beans from Colorado or you're eating beans in Puerto Rico, you're getting a different level of iron intake. Last example, multivariate analysis of dry powders. This was a project in association with US Pharmacopoeia. The idea was to have a universal global standard for a milk powder that could be used to look for adulteration. In other words, you have a reference milk powder, and if your milk powder looks different, has it been adulterated? That would be the starting premise. So there were several factors here. Milk class, non-fat dry milk versus skim milk powder, sorry. Day of analysis, we found a difference there. You can see, if you look to the far right, you can see the statistical variability, significance. So milk class was important, very important. So was the day of analysis. Processing temperature, they had used a high, medium, and low heat. It varied according to plant. It was significant. Production site, 14 sites across 8 countries, very important. Sample, between samples was significant, and milk, the cross variation was important. So what this showed us, especially with the production site being so significant, is that a local reference material is much better suited for detecting adulteration than an international global standard. Now, what are we going to see when we go to Foundation Foods in FDC, the Food Data Central? This is a table taken from the database, and this is the glucose concentration in ripe and slightly ripe raw bananas. So you can see we've got a listing of 12 samples, if you count them, and the NDB number, and it gives the method of analysis is the same. It gives the city, state, acquisition date, and then obviously on the far left, the concentration. You can see one down here about 0.025, a less than value. So is it a flyer? Hard to tell. How can we display this data that will be meaningful? Well, most of you are probably familiar with the database of standard reference that we've used for years and years from USDA. It would give you a mean, a min, minimum, and a maximum. And you can see these values listed here, the mean in red. This was from SR, the old database, 8 values. Now, here is a possible way of representing the data to illustrate the variability. So what we've got is a vertical line for each sample that was analyzed. Again, the mean is in red, but you can see the distribution of these samples. Here's the maximum and here's the minimum, which was at limit of detection, less than value we saw. And because it's a less than value, it's dashed as opposed to a solid line. Now, if you look at this, you would say, okay, the food glucose in bananas as I buy them on the market have a fairly large degree of variability. Now, are these numbers individually different? Intuitively, you could say, well, this one is different from the mean and max is different. But What's important is the confidence interval. In this case, the confidence interval was 0.2 in terms of concentration, grams per 100 gram. And you can see then I've illustrated the confidence interval width is this interval here at the top. So some of these samples will be similar with respect to the confidence interval. Most will be different. So we can look at this and say this is the biological variability we found in bananas in the marketplace. Is this a flyer, this less than value here? We'd have to we did rerun the sample and it was still a less than. So I don't know which banana that was, but it obviously wasn't very sweet, low in glucose. So in summary, there is considerable variability of all components in foods. And it's certainly not going to be obvious to the consumer as they purchase these food materials, these commodities in the marketplace. For research purposes, it's important to characterize variability. And the variability arises from genetics, environment, management, processing, and preparation in the home. So Foundation Foods is intended to measure variability of single ingredient foods. This does not, we do not cover complex food mixtures, you know, your beef stew or whatever. Those would be covered in the branded foods database. Foods are identified and defined, sources of variability are identified, and samples are collected and analyzed individually. So, display of data is important. We want to provide the simplest means of communicating variability. Thank you very much for your attention. That concludes my talk.
Hi everyone, I'm Linda Cantor, an economist with USDA's Economic Research Service, Food Economics Division. I'm going to talk with you today about the ERS Food Purchase Groups, a food grouping system that we've been working on at ERS for the past 15 years or so. But before I go any further, I'd like to recognize my colleagues in this effort, Alina Page and Andy Carlson, both with ERS, as well as Mary Muth, our contractor in this effort from RTI International. Many of you are likely familiar with some of the different ways that USDA groups foods. The What We Eat in America food categories are used to analyze foods and beverages reported in the What We Eat in America survey. USDA's My Plate group synthesized dietary guideline recommendations to guide America's food choices. The USDA food plan, such as the Thrifty Food Plan, are market basket categories that group foods by nutrient density and cost to guide consumers in making food choices that align with the dietary guidelines and budget constraints. The ERS Food Purchase Groups, or EFPGs, are an innovative food classification system that considers the form in which foods are purchased, such as fresh, frozen, and canned, and its relationship to diet quality. The EFPGs aid researchers in sorting millions of food items as purchased from household panel and retail scanner data into food groups for policy-based research. The EFPGs support research on the economic determinants of diet quality and health outcomes. They provide insight into how consumers balance food choices with time constraints, dietary restrictions, tastes and preferences, and cooking and preparation skills. They capture price premiums for convenience and processing. And using the EFPGs, researchers can study policies that affect specific categories of commodities, such as subsidies for fruits and vegetables, or taxes on certain beverages, such as sugar-sweetened beverages. As I mentioned at the outset, ERS has been working on developing the EFPGs for quite some time. The first food purchase groups were developed by our ERS colleagues Jessica Todd and Lisa Mancino for use in the quarterly Food at Home price database. They used supermarket scanner data to develop household-level quarterly retail prices for 52 separate food groups across 35 market areas. Lisa further expanded the groups for the National Household Food Acquisition and Purchase Survey, or Food Apps. The ERS Food Purchase Groups expanded the Food Apps groups to 90 categories to reflect the larger volume and variety of foods reported in household panel and retail scanner data. The EFPGs are structured into 3 distinct tiers. Tier 1 starts with the 5 MyPlate food groups: grains, vegetables, fruit, dairy, and meat and other proteins, consistent with the dietary guidelines. The 6th group, other foods, captures foods that are typically contributing to discretionary calories, including fats and oils such as butter and salad dressing, desserts, sweets and candy, cake and cookie mixes, and savory snacks. We also know that many foods purchased for consumption for home are in forms that reduce or eliminate preparation time for households. For example, canned soups, frozen entrees, and other mixed dishes are available ready to heat. We know that this segment of the consumer market is growing as the line between supermarkets and restaurants is becoming increasingly blurred, with supermarkets offering hot food bars and other ready-to-eat foods. So the 7th Tier 1 group, prepared meals, sides, and salads, captures convenience and commercially prepared mixed foods. Now I'll go into more detail. Each of the 5 major food groups in Tier 1 were broken down into Tier 2 specific subcategories, consistent with the dietary guidelines. For example, since individuals are encouraged to make half their grain foods whole grain, the grains group is separated into whole grains and refined grains. In some cases, however, the EFPGs add additional subcategories. For example, the vegetable group includes all the healthy eating pattern subgroups from the dietary guidelines, except that the EFPGs add 2 additional groups, tomatoes and potatoes. The goal of this division is to separately identify the most frequently purchased types. For example, in 2019, potatoes and tomatoes accounted for 52% of total vegetables available in the U.S. food supply. By contrast, the next 2 vegetables, onions and sweet corn combined, accounted for only 10%. The prepared meals, sides, and salad group is further broken down into 4 subcategories: ready-to-eat foods, frozen, refrigerated, ready-to-heat foods, shelf-stable, ready-to-heat foods and soups, and shelf-stable meal kits. Again, the emphasis is on the way in which foods are purchased rather than consumed. Foods in this group are often composed of multiple ingredients, making it difficult to separate the items into distinct categories. The dietary guidelines recommend limited intake of saturated fat, added sugars, and sodium. Often these foods and nutrients are added in food processing. For example, canned and frozen vegetables are often pre-cooked and have added ingredients like sodium. This motivated further division of the EFPGs into a 3rd tier that distinguishes between raw or fresh and products with additional processing. This slide shows an example of Tier 3 categories for the vegetables group. I want to draw your attention to the fresh cut vegetable group, which captures the value added to pre-cut broccoli florets and trimmed and washed salad greens, distinguishing the products from the less processed fresh foods shown on the left. The rotisserie chicken highlights the way that the EFPGs capture consumer demand for convenience and processing. In the EFPG structure, a rotisserie chicken would be grouped under the Tier 3 category, prepared foods that are ready to eat, rather than the meat and protein group, which would be limited to fresh and frozen chickens, needing additional cooking and preparation time. In this slide, the multiple ingredients and convenience of a fresh fruit tray with cream cheese dip would put it in the ready-to-eat subgroup, in contrast to the sliced mangoes shown on the right, which would go into the Tier 3 group for fresh cut fruit. Now that I've given you an idea about the basic structure of the EFPG groups, I'm going to talk a little bit about some of the research applications. As I mentioned earlier, the ERS food purchase groups were first created to support the development of the Quarterly Food at Home Price Database, or QFAP. The QFAP provided quarterly household level prices per 100 grams for 52 food purchase groups and 35 market groups across the United States using UPC-coded products from a panel of 40,000 households. The purpose of the database was to provide researchers with a tool for studying how prices affect food choices, food intake, and health outcomes, and capture geographic variations in food prices that reflect proximity to point of production, availability of different types of food retailers, and socio-demographic characteristics of a market area. This chart shows the variation in prices across 4 regions in the U.S. for selected food purchase groups for vegetables. ERS is currently in the process of extending the QFAP work to create a new series, the Monthly Food at Home Price Database. This database will provide average prices and price indices for 14 geographic areas and 92 ERS food purchase groups, or about 600,000 UPC-coded food products annually, using prices from the IRI InfoScan store-based scanner database. Mary Muth and her colleagues at RTI International have mapped UPC codes to the ERS food purchase groups using IRI data for 2016 to 2018. ERS researchers have also used the food purchase groups to calculate food pattern equivalence and HEI scores for food acquisitions and purchases reported in the 2012-2013 Food App Survey, led by our ERS colleague Lisa Mancino. This table shows the sodium content and the percentage of calories from empty calories across the Tier 2 whole grains and refined grains groups. This work differs from the QFAP research in that the food app households reported foods that they purchased for food at home from supermarkets, as well as food away from home from restaurants and other places, and foods acquired for free from school lunches, family and friends, charitable food assistance, and other places. This chart expands the analysis and shows the sodium content of a more diverse range of foods. Not surprising, the salty snacks as well as prepared foods are among the top sources of sodium, along with meat products, which include bacon, sausages, and hot dogs, deli meats, and smoked fish. In conclusion, the ERS food purchase groups classify foods in relation to their main ingredient, quality, and likely price premiums for convenience and processing. The groups are hierarchical and meant to be flexible. Researchers can regroup as needed within categories. For example, they can select the relevant IRI InfoScan product codes for use in analyses such as total dollar sales or average prices by EFPG. I'm happy to answer any questions now, or if you think of questions later on, my email is listed on the slide. Thank you very much.
Thank you and good afternoon. The title of our presentation is The Impact of Using Different Versions of the USDA's Food and Nutrient Database for Dietary Studies, FNDDS, on nutrient index of the U.S. population, enhanced 2015 to 2018. All the co-authors of this presentation are from the CDC's National Center for Health Statistics, the Division of Health and Nutrition Examination Surveys. Research studies often estimate macro and macronutrient intakes using FNDDS nutrient values from the past. This is because dietary data are collected continually, thus may not correspond with FNDDS. We, using data from the National Health and Nutrition Examination Survey, examine the potential bias of this practice on nutrient intake estimates. The National Center for Health Statistics, NCHS, is responsible for the enhanced survey sampling methodology and data collection activities. The ENHANCE is a complex multi-stage probability sample survey to select a nationally representative sample of civilian and institutionalized population in the U.S. to monitor the health and nutrition status of the population. It is a cross-sectional survey. Participants are not followed longitudinally. Data are collected and released in 2-year cycles. The 2-year cycles chosen for this analysis are the 6 most recently released cycles from 2007 to 2018. Enhance is conducted in 2 major parts. Participants are first interviewed in their home through an in-home questionnaire. And follow-up exams, lab sample collection, and the first 24-hour recall are performed at the Mobile Examination Center, MEC. In continuous Enhance, the USDA and the HHS integrated their data collection efforts on dietary assessment into a single survey called What We Eat in America. The USDA has a primary responsibility for the development and maintenance of the automated dietary interview system, dietary data processing, and the maintenance of the technical databases that are used to report the dietary intake findings. For these analyses, data from the first 24-hour recall collected during the MEC were used. Briefly, trained interviewers collected dietary data using the USDA's Automated Multiple Pass Method, AMPM, for collecting 24-hour recalls. They used standardized probes to minimize misreporting of amounts consumed. Survey participants 12 years and older completed their own dietary interview. Children 6 to 11 years were assisted by an adult, and proxies reported for children 5 years and younger. During enhanced dietary data preparation, reported foods and beverages are marked to the USDA's FNDDS for that survey cycle to get nutrient intakes. The FNDDS food codes are accompanied by food descriptions, ingredient lists, and gram weights for each food and beverage reported, which allow for the computation of nutrient intakes from all the foods and beverages consumed. The FNDDS is updated for each 2-year enhanced survey cycle by our USDA partners at the Food Surveys Research Group to include all foods and beverages reported during that survey cycle. For each new version of the FNDDS, the list of the foods and beverages, the portion sizes, the nutrient values are reviewed and updated. New foods are added to the database based on changes in consumption and the marketplace, and some foods are discontinued. As mentioned earlier, researchers may use older versions of the FNDDS in their studies to compute nutrient intakes, and this may introduce bias in their estimates. For example, for a study conducted in 2015, the most recent available FNDDS would be the 2011-12 FNDDS version, since it takes time to thoroughly update the databases. And in using this older database, imprecision in nutrient estimates may be introduced due to missing food codes for new foods since the 2011-12 FNDDS, and also nutrient values might have changed. Therefore, we examine the potential bias of using older versions of FNDDS using enhanced data from various cycles. There were several specific objectives, and I will present them in 2 parts. For all objectives, we used FNDDS preceding the enhanced survey cycle, asynchronous, versus the one corresponding to the survey cycle, synchronous. For the first set of objectives, we assessed the number of unique food codes that participants reported in Enhanced 2007-8 through Enhanced 2017-18. We also examined updates to the food codes by looking at the number of newly reported food codes in Enhanced 2007-8 through Enhanced 2017-18. We then estimated the proportion of the newly reported food codes as a percentage of all reported food codes. For the second portion of our analysis, we examined changes in nutrient values in FNDDS, comparing the 2013-14 FNDDS nutrient values to the 2015-16 FNDDS nutrient values for the same foods, and we also compared the nutrient values for FNDDS 2015-16 to those of 2017-18 for the same foods using concordance correlation analysis. With an estimated and compared mean nutrient intakes for enhanced 2015-16 based on the 2015-16 FNDDS and the 2013-14 FNDDS, and also estimated and compared nutrient intakes based on the 2015-16 FNDDS and the 2017-18 FNDDS for enhanced 2017-18. Given enhanced as a complex survey design, specific methods were required for proper analysis. We used day 1 dietary sample weights to account for an equal probability of selection, non-response, and day of the week of the recall. We used Tyler series linearization to estimate variance. And for statistical testing, we used t-tests for pairwise comparisons with Bonferroni's correction for multiple comparisons. Finally, we used concordance correlation analysis to compare nutrient values from the different versions of FNDDS. For the first portion of our analysis, we included all available dietary data from all participants from Enhanced 2007-8 to Enhanced 2017-18, including data for children reported to be breastfeeding. Here are our results for the first portion of our analysis. We looked at the number of unique food codes reported in each enhanced survey cycle and found that the number of unique food codes increased from 4,255 in 2007-8 to 5,085 in 2015-16. Next, we determined the number of newly reported food codes in the enhanced survey cycle. To do this, the enhanced 24-hour recall individual food files were merged with the preceding FNDDS nutrient values and nutrient descriptions, and resulting food codes with missing nutrient values were considered to be new for that survey cycle. We found that the number of newly reported food codes varied from 186 in the 2007-8 enhanced to 745 in the 2015-16 enhanced. We then estimated the proportion of the reported food and beverage items that were missing in the previous version of the FNDDS, that is, the new food codes, as a percentage of all reported food codes, and found that they varied, ranging from about 4% of all reported food codes in the 2007-8 enhanced to as much as about 15% in the 2015-16 enhanced. We also estimated the proportion of participants who reported consumption of any of the new food codes and found that they varied from 18% in the 2007-8 enhanced to almost 74% in the 2015-16 enhanced. Using the dietary data from enhanced 2015-16 and enhanced 2017-18, we looked more closely at the newly reported food codes. To determine the new food codes, the reported food codes in enhanced 2015-16 individual food files were compared with food codes in the 2013-14 FNDDS and reported food codes in the 2017-18 individual food files compared with food codes in the 2015-16 FNDDS. For enhanced 2015-16, food codes that were found in both 2013-14 FNDDS and the 2015-16 data were dropped, and for enhanced 2017-18, food codes that were found in both 2015-16 FNDDS and 2017-18 data were dropped. The remaining food codes were considered new and were categorized based on what within America food categories. The categories of the foods varied slightly in the two cycles as shown. The selected categories were found in both cycles. Also, the number of participants reporting the new food codes varied, which may explain the overall higher number of participants reporting new food codes for 2015-16 compared to 2017-18.
As mentioned earlier,
Nutrient values in the FNDDS databases are reviewed and updated. We examine the correlation between nutrient values for the same food codes from a preceding FNDDS to nutrient values from the database corresponding to enhanced survey cycle. We found that nutrient values in the 2013-14 FNDDS and those in the 2015-16 FNDDS for the same foods corresponded by at least 99%. We also found that nutrient values in the 2015-16 FNDDS and those in the 2017-18 FNDDS for the same foods corresponded by between 94% and 99%. The next set of slides present findings from the second portion of our analysis. We included data for participants aged 2 years and over from the 2015-16 and the 2017-18 survey cycles with reliable dietary records. We excluded 179 participants whose records were unreliable, 13 participants who were reported to be breastfeeding, 1,808 whose records were not collected at the MEC, and 905 participants who did not go to the MEC. Our final sample size was 15,040 participants. We compared estimated intakes for 29 nutrients. Mean intake estimates for enhanced 2015-16 were based on the 2015-16 FNDDS and the preceding 2013-14 FNDDS. And mean nutrient intake estimates for enhanced 2017-18 were based on the 2017-18 FNDDS and the preceding 2015-16 FNDDS. Day 1 individual food files for enhanced 2015-16 were mapped with FNDDS 2013-14, and those of enhanced 2017-18 were mapped with the 2015-16 FNDDS. We found that using the 2013-14 FNDDS with the 2015-16 enhanced resulted in estimated mean intakes for all the 29 nutrients lower by between 5 and 30% compared to those based on the synchronous 2015-16 FNDDS. Similar patterns were seen by sex, age, race and Hispanic origin, and by income. For 2015-16, all these mean nutrient intake estimates based on the 2013-14 FNDDS were significantly lower than those based on the 2015-16 FNDDS. For enhanced 2017-18, mean nutrient intake estimates based on the 2015-16 FNDDS were lower by between 0.1 to 8.6% compared to those based on the 2017-18 FNDDS. Nevertheless, mean nutrient intake estimates for monounsaturated fat, vitamin E, vitamin C, vitamin B6, folate, vitamin B12, sodium, zinc, copper, and caffeine were not significantly different from those based on the 2017-18 FNDDS. Overall, mean intake estimates were lower by between 5 to 30% using the 2013-14 FNDDS for enhanced 2015-16, and mean intake estimates were lower by between 0.1 to 8.6% using the 2015-16 FNDDS for enhanced 2017-18. And similar patterns were seen by sex, age, race and Hispanic origin, and by income. Our study had some limitations, including the dietary intake assessment in ENHANCE rely on recall. However, the AMPM method used in ENHANCE has cues to prompt respondent memory while reducing respondent burden to obtain accurate recalls. Also, these analyses were based on synchronous versus preceding FNDDS. Versions older than the preceding FNDDS were not compared with synchronous databases and may give greater bias in nutrient intakes. In conclusion, Even though nutrient values in the databases may only change slightly for the same foods over the years, for example, comparing nutrient values in the 2013-14 FNDDS to the 2015-16 FNDDS for the same foods, where we saw the 99% correspondence, use of an asynchronous older version of FNDDS to obtain nutrient intakes underestimates nutrient intake, and this is overall and by key sociodemographics. The level of underestimation corresponds with the number of new food codes in the databases, and this could be substantial over the years. Thank you for listening.